can't beat the in-person interactions, the lunches, the dinners. The quality of the people that you meet over coffee here is just phenomenal.
Welcome everyone to Almost Always Vector, which used to be named Almost Always Vector, but they said the question mark was, not deterministic, so it's Almost Always Vector. I'm excited to give this talk. It's, my goal is to convince you why 80% of the time, especially if you're new starting out, vector is the container and the structure you want to go to. So, as I was finishing up slides last night, I found this Reddit, which, my professor is telling us to never use vectors. And I'm glad I didn't ever take that CS class. We'll get to that in a while, but evidently it was a very popular, I couldn't copy the whole thing because as you can see, this was the third edit for the original poster. And there was about 400 responses in the comments underneath. And most of it was generally like, why would you not use vector? And so we'll show some of that. All right, so we're kind of looking at some basic code here. Line 5 is the way that we used to do arrays, right? It's static. Actually, can anyone tell me the bug I got here? If I was making an array, say cpplusplus98 on line 5, do you think that would compile? I mean, it's an initializer list, but I am missing my size, right? And so I probably have other mistakes in the slides. I do have the code. It's going to be up on GitHub, so everything that's on here you'll be able to pull down and play with. But we'll see in a few minutes why I want you to keep an eye on and help me find some mistakes and shout out. You can heckle me. I'm okay with it. So anyways, I just look at line 10 and 11, I'm like, the C-style way of getting the size of something was even harder than just using a vector. And this doesn't even get into the fact that, one is stack allocated, one is heap allocated, and all these other fun things. But if you want to look at that Reddit thread, there's a link to it down there. So, more on std vector. I came up with the idea for the talk before I actually did the search on std vector. And as you can see, there's 1 or 2 videos on std vector, or 3 or 4. Or I actually stopped it at that point, but you can see Google was well lined up to give me plenty more std vector talks. So I'm just hoping to have fun with this one. How many of you are still, I'm going to age myself here, like when I was a kid, I could pick up a book, and I could start on page 1, and I would enter in every problem, everything as I went all the way through. How many of you still do that? Okay, I'm getting no one. Seriously, no one does that, right? Okay, so how do I read a technical book front to back now? By becoming a technical editor. That's how you get it done, because you have to read it front to back. And so this book from John Ferrier is Data Structures and Algorithms with C++ and STL. This was part of my inspiration for doing the talk because I think it's a great book. He goes through and it's not an in-depth book, right? It's not going to give you all the deep details about things, but it gives you that great overview of all the different container types, how to use them in different algorithms, covers pointers, covers allocations. And so when I saw that, I'm like, this would be fun to do, even just part of this. Now, the fact that I got the book on there, Pact was kind enough to send me some copies. So if you find an error, raise your hand, point it out, win a book. I have 2 of these ones, and then I also have a performance book from Fedor, who's actually here teaching classes this week too, and it's also for sale. So if you want a book, find my mistakes. So the old way. So this is where I was saying, default initializer list, at least in C++, prior, in the old 98, you would at least turn around and say, okay, well, I have, 6 pieces of data. You stick it in the initializer list. It's pretty plain what we expect this is going to do, right? It's just going to print out the years that we have there. You notice I call this CppCon the early years. So the early years would be back when we were in Bellevue. There's a point to this. Because now, 2019 was our first year here. But I can't just delete the 2019 because it's an array. It's a fixed data size. The best I could do is zero it out, which I can do. And back then, if you really wanted to make sure to not see it, you could probably write an if statement to say, well, if the value is 0. But having a fixed length data member as your only way of doing things before was kind of limiting. And that's just one issue, right? If we turn around and look at some of the other limitations, so as we showed there on line 5, you can't really do a delete. Of course, you can't just sit there and add on an extra item as I show on line 6. It's not like you can just add 2020. And to actually get anything to move around, it's like if I really wanted to delete the 2019, I would have to create a new array. Then, because the way arrays work, you can't just sit there and do a copy or an assignment straight across. You literally have to do a for loop and assign each item across. And again, this is still all talking about the stack. This has nothing to do with the way that we used to have to do if you want to do it on the heap with new and delete or malloc. And so, of course, in the end, we get our printout here, which is a little weird. Anyone want to take a guess for a book at why we get down to the 1 in the 2014? Okay, I know it's after lunch. Yes?
The length of the revised the length of the revised list is still 6, but we haven't copied 6 things.
Okay, and can you see the second part?
Garbage values in there?
Yeah, we're actually reading off the end of the array, right? Because in line 15, I'm reading through 7 and not just through 15. Or, yeah. Thank you very much. So, and this is the other part that I loved about the old way we used to do things. Like, you are more than welcome to take your foot off, right? That's kind of the thing with C++. You're welcome to shoot your foot off if you like. The ability's there. And so this is the way that we used to be able to do it. And it was error prone. When I hear people talk about safety issues, generally it makes me think of older C++ as we used to call it, right? So when I wanted to find out more about where this all started, I did some searching and I found the original paper from 1992 from Uwe Steinmüller and Alexander von Zitzwitz. Why are dynamic arrays needed in C++? So arrays are widely used low-level abstraction for storing elements of a common type. C++ provides arrays as a built-in type, so why would one want to implement a generic array class? There are basically the following reasons. So C++ does not provide dynamic arrays. We've seen where that's kind of a bummer, if you're having to recopy and do all of that boilerplate time and time again. And so because of the fixed size limits and maximums that are set at compile time, C++ does not support copying or assignments. We saw that. And generic dynamic arrays are important building blocks for the implementations of many other kinds of classes. And nearly every serious application will need it. And we'll see that's true. I do think it's kind of funny, this last line in their first point. On the other hand, using dynamic arrays in C is error prone and boring. The boring part made me laugh. Okay, how many of you have had to use new and delete? Okay, how often have you not been worried about getting it wrong? Okay, that's me, like I know I'm gonna point someplace wrong, so it wouldn't be boring for me. It'd be like sitting on the edge of a well, wondering what I was gonna do wrong with that, And so you're starting to get an idea why I like vector. Things being abstracted away, I'm okay with that. All right, so here's our plan. We're going to talk about the basics. Then we'll do a little bit on memory management, cover some of the ways that the back end happens so we can learn a little more about it. I'm going to lightly touch on some of the key parts of iterators that have haunted me and how I've learned from them. Then we'll look at a couple algorithms, specifically with std vector. And then we'll do a couple container comparisons. And we all know that there's a ton of containers, so we're only going to touch on a couple of them. And then I'll see if I can convince you why I think we should almost always use vector. So the basics of dynamic array. How many of you love templates? Okay. Walter, I did see your hand, right? For the note, that was probably less than 10% of the room. And I'm right there with you. I do like this template because I can still understand it, right? You know, it's like, okay, we got a default constructor, you know, we can do the size, we got the destructor. This is nice and simple. And this is what the original specification was in the paper. I just copied it out of the scan because I figured it'd look better in this form. And so it was kind of funny because when I was on LinkedIn, I started to try to find the original authors, and I actually found Alexander. And I'm like, oh, this is so great. I get to talk to the person that wrote the paper. Hey, I'm doing this talk on vector at CppCon, you know. I wanted to talk to you about a paper you wrote. It's like, are you sure it was my paper? And I'm like, yeah, it was the one in 1992. My gosh, that was like 32 years ago. But he did say that the reason that they came up with dynamic array was for the exact kind of thing that I've been talking about we're trying to solve. You know, arrays, especially back at that point in time, they were just static. If you turned around and had something where you thought you were only going to need 10 cells and suddenly you needed 20, well, you were having to recompile or find some other way to manage that. It wasn't as easy as it has become. And so for them, they were using this as the base class for many parts of the backbone for their collection classes, including strings, which, you know, back then everything was a character array. But he does point out that as the 2000s came around, everyone moved to the STL, and for good reason. And so it got let go after that. So we started with dynamic array, but then it turned into vector. And it was also interesting, I saw in the paper that they were choosing dynamic array because of array was a built-in type, and they didn't want to use the alternative of vector because it had too much of a mathematical connotation. And I was talking with John Kolb about this a bit because the thing that's interesting is there's a lot of words that we use in C++ that when we're talking about things, it's like, you know, I have this concept about something, and then it's like, well, wait, are you talking about a concept for a template, or are you talking about a concept as just something in your head? And so it makes me think of Kate Gregory's talk that she gave, which is like, naming is hard. But in the end, Stud Vector was born, and here we are today. So in 32 years, what has happened? This was kind of that synergistic thing. We've actually had 32 member functions added. It was a good time to do the talk. So there's more ways to access elements, you know, and I know it's probably pretty tiny over there, but I think most people are pretty in tune with CPP reference. But now we have at and front and back and data, and we have iterators and allocators and modifiers. Oh my. So now we'll look at the basics of actually stud vector and not dynamic array. So there's lots of different ways to create a vector, right? We have the empty vector. So in the case of line 5 there, we're just doing a default initialization of an empty vector of shorts. I picked a short because I'm pushing back years. And so this is the Washington years, 2014 to 2018, when CppCon was there. And then we have the Colorado years, 2019 to 2024. You can also turn around, as we show in line 16, you can actually just create, you know, a vector of the total amount of years that you want in it. And there, we'll get back to why this is kind of an important thing and has to do with memory allocation. And if you want to fill it up with a default value, then hence CppCon space Odyssey, where we have 11 times of 2001. In the end, does anyone want to take a guess at what we're going to get on the output of total years? Ah, yes. That's exactly right. Default initialization of the value inside of it, right? Okay. So accessing data in a vector has, you know, gotten easier as well. So we do have your index operator. So we see CO years there where we're accessing the first element. You have CO years front, which will also access the first element. And then we kind of do the same thing with back and then using at. At does similar to what the brace initialize or the brace accessor does. And so, the output turns out being kind of what we would think, 2019 to 2024, and then, all of our years in between. So if we have the brace, or the index way of accessing things, then why do we have at? And so I trimmed this down a little bit just to show, because when things work, you have the Colorado years 0 and Colorado years at 5, which is going to give us the first year and the last, right? But what about if we try to do this? Now, obviously, they're both out of bounds. But when we run this, line 9 and accessing with an index, because it's C++, it's just happy to do that for you. However, if you use at, it will throw an exception. And so that gives you the ability to try to catch an error. So if you're getting an array and you're not sure of the size, you can make sure the value's there. There's a lot of different structures in the standard library and a lot of different features. Features not quite the right. But for example, we use at even for nLoman's JSON library. By using at, you can actually look to see if a value exists, because it will turn around and give you the ability to catch an error, which, if you're dealing with something like JSON, where you're getting in a JSON packet with all kinds of different keys in it, you may or may not know if you have the key available. So at, to me, is a very useful function. I get to use that one a lot. So also, we have .data for accessing, and .data is, I liked this example of it. .data is when you want to see. And I say it that way because if you're interfacing with any kind of a C library, .data does a great job of getting you that raw pointer, which is normally what a C library wants to see. And so in this example, we start off with a regular vector, but when we call co years.data, we're actually getting a pointer to the start of the structure. And then we can actually do the pointer type arithmetic that we would normally do to either output it, or as we see there in line 12, to be able to change a value inside. And of course, in this case, I'm trying to overwrite 2020 because the Colorado years, we kind of didn't make it here for that one. So the output ends up being, what we would expect. So if you ever do need to access with a C library, OpenSSL comes to mind for me a lot. Unfortunately, then .data is a good way to get what you need. And .data isn't just for std vector either, right? You can actually do .data on a std string. So a lot of the container types have .data to be able to get the same thing. All right, so we'll look at some memory management now. So stack versus heap. All of the examples I was kind of showing beforehand, we're looking at it like, here you see on line 6, we're initializing this array on the stack. Line 7, of course, is doing a std vector. So that's not initializing on the stack. That's initializing on the heap. But it's so clean. It looks just the same as the line that's above. There's also no new and delete. This is inside of a function. I mean, granted, this is main, but if it was inside of a function, the cleanup would just happen automatically when you exited anyways, right? And so in our case, Bellevue in our early years is 2014 to 18 again, and then we have our Aurora years. You'll notice in the early years, I'm doing a for loop, whereas in line 14, I'm using the for each, or the ranged for loop. And there's kind of a funny thing about that later we'll get to. That is not an iterator when you're doing a for loop that way. So our output, again, kind of as you'd expect, no surprises there. But the problem we have with the stack is its size, right? There's only so much that we can put on it. And one of the ways you can find the size limit, if you're on a Linux or a Mac machine, is this ulimit -s. But I was like, well, that's not really a lot of fun. I mean, ulimit -s will tell me what it is. How about smashing the stack? So if you look here, we have a nice little recursive call that's going to create a 1K buffer on the stack and keep calling itself until it blows up. And so at least on my MacBook, that happens after about 7,800 times, which gives me about an 8 megabyte stack. And incidentally, when I did u limit minus s, it also comes out to be about the same. And so this is, we have lots of very fast access with memory on the stack, but at the same time, we're limited to how much we can put in there. And there are a lot of functions that we write where we don't need, a lot of memory access. I work in the credit card business, and we process billions of dollars a month. And so we're generally working with data that takes a lot more than the stack can hold. And we'll look at that later too. So the trade-off, on the stack, it's fast, right? Because in order for you to get more memory on the stack, it's just, all they're gonna do is adjust the stack pointer. And so getting new items on the stack happens very quickly. It's automatic. The stack is for basically the function that you're in. Once it's out, it cleans up. It's easy, at least to me, it's easier to debug because I can reason about it a lot more. Locality-wise, cache performance. When you're pulling things up on the stack, you're able to get better cache performance because of the location of where memory's at. There's not as many jumps for it to reach a particular spot in memory. And then on the safety, I say the automatic. I don't have to worry about if I left something dangling. It just cleans up on the end. On the heap, we have flexibility because we can dynamically allocate the amount of memory that we need at runtime. If I pull in a file that's 10,000 items long, then I can allocate 10,000. If I pull in a file that's 100,000, I can allocate 100,000, and I just get it right then. It's large. Bigger's better, right? At least depending upon the amount of data we need to process. With the amount of things that we keep on our phone, I think generally we always need more memory. How many people can fill a 1 terabyte hard drive faster than they used to be able to fill a 320 gigabyte hard drive? Yeah, more space is more stuff. Lifetime of the heap is not function dependent. So that is one of the benefits. If we allocate something on the heap, it doesn't have to be cleaned up at the end of the function. And then sharing, you can share on the heap between two threads. Not quite, I think thread local might be able to do something with that on the stack, but generally speaking, it's easier to do between two threads. So for the stack, use it when the data is small, doesn't need to persist beyond the function, and when you want speed. On the heap, use it when the data is large and needs to persist, and you need flexibility. But always remember when you're doing stuff on the heap, watch your toes, because I've worked in a lot of code bases, especially older ones, even things that we take over. It's like 360,000 items in an old array that literally used pointer arithmetic, and if you didn't run off the end, and if you weren't careful, you would turn around and read in spots that you weren't supposed to, or leave something dangling and not get cleaned up. The other thing about heap, that I don't have in here is reallocating on the heap gets more expensive, of course, because you can create memory fragmentation. And so when you're trying to allocate now another larger block of memory, it has to find a spot where it can get that contiguously, at least for std vector. Other data structures don't necessarily need the contiguous memory, but std vector does. And that's one of its benefits, is that it is contiguous. So with std vector, part of the way that we help manage allocation is, I want to look at it, there's two features. There's size and then there's capacity. So the size of the vector is the amount of items that are in it. The capacity is how many more items can go into it. In some cases, how many more items can go into it before it reallocates. So in this case, we're starting off with 6 items in our vector. And I start there just so we can show the size versus capacity. But then we initialize this vector Washington, and we're just going to push back 1 item at a time. And so when this runs, you see that the first one, the size of Colorado, is just 6 and 6, right? That's how we initialized it. It created the exact size we would expect. However, for the Washington one, as we start to step down and add 1 more, finally, by the time we're doing that 4th add, it's like, oh, he's probably going to add some more, so I should probably allocate more memory and have a higher capacity. So in essence, when we went from size capacity 0, 0 to size capacity 4 to size capacity 5, each one of those was a reallocation. Finally, there on size 6, it was another reallocation, but when it reallocated, it actually left room for me to add 1 more. If I did 1 more push right now, it would not reallocate. It would just take and fit. And so When we're talking about small sizes like this, of course, the allocations, it's minuscule, but we don't work on toy examples like this. This isn't what we do on a day-to-day basis. But this was one of the simplest ways I think I could find to show this, where capacity starts to kick in. So part of the reason why I love stood vector, and I think everybody should, is because we don't have to do this anymore. This is how it used to have to be done. So we would create a pointer to an array of ints. That's our C array there at the top, right? And there's our new. So what you knew, you must delete. Otherwise, you get a dangling pointer and leaked memory. So then in the loop, we end up just assigning a value to the 5 pieces of the array. And I don't know about anybody else, but the amount of times that I found code where either I walked off the end of the array filling it or someone else did, especially if I go back to about 2014, it's almost shameful. But then if we want to grow the size of that array, well, now we need to make a new temporary array pointing to a new block of memory that's going to be larger. And we have to copy all of the data over. Then we delete the original, and then we reassign from the temp. So every time that we do an allocation, or every time you see vector do an allocation, this is what it's hiding. This is what you don't have to worry about writing. You just say push back, and vector takes it and works on doing all this reallocation for you in the back end. You don't have to think about it. You don't have to think about, did I leave a dangling pointer? Did I leak memory? It just handles it for you. Of course, the output's really no surprise. The point of the example is more about what we do in reallocating and what we no longer have to do thanks to the standard library and things like stood vector. So managing allocation. So now that we know how the allocation actually works, what can we actually do about that? And so here again, I'm just going to show a little bit, another run of this. So we're going to start off, let me back up. So at the top there, I got a small function that all it's going to do is push back. And I put this into a function simply because of saving space on the slide. It's easier to push back a group of items this way. So we'll start off in Colorado 2019, and we're going to look at CppCons into the future, right? So we'll start off with the first 4 years. We'll get a look at the size and the capacity. We'll add on another 6 years. And you'll notice that I'm using CO back. So I'm actually going to take the last item from the vector and use that as my starting value as I pass it into the function so that we continue just adding on years. So as we run this, we see that the first one starts off with a size of 4, which that's our initial pushback. When we do our next run, we'll notice that it automatically already allocated more in capacity because it's expecting more growth. Now, I actually opened up the standard template library header for stood vector. And again, like I said, I like the dynamic array template a lot better to look at and read. However, I do appreciate the magic of it taking a really good guess at what it thinks you're going to reallocate next. And so as it's pushing back, however the algorithms work for the maintainers of the standard library, they've spent a lot of time optimizing allocations inside the containers, inside the STL, so that we can depend on them to do what we need them to do. And finally, with the last resize, it does, yet again, it does another resize. So in order to prevent allocations, though, we have the reserve word. And that is probably one of your best ways to make vector more efficient. If you have any idea of how much you're going to put into a vector, you can simply reserve it. And so here you'll notice that we start with our initial pushback of 4, but then I know I'm going to push back a bunch of years. And so with that being the case, I tell it, hey, I want to reserve 40 more slots. And so when we run, you'll notice that yes, we get the first, insert of 4 with a reallocation. But then once we do the reserve, we're no longer reallocating. We're just filling in that space that's already there for us. And so if you're actually doing a lot of work in a vector and you're finding it maybe not as performant as you want, this is one of those items you can look at doing. Can you estimate how much space you're going to use? If you were loading in a file, can you look at the file and say, well, I know my records are about 100K, it's a 16 megabyte file. I need to pre-reserve this amount of memory. And then at least get yourself halfway there. So the opposite of reserve is shrink to fit. You know, if you turned around and have a bunch of capacity allocated and you know you're not going to need it, you can also ask Vector to release it. Now, the one thing about shrink to fit is that it is not a guarantee in all implementations. What I mean by that is it will turn around and shrink your size and capacity, as we can see here. What it won't do, because we started with the size of 32 and it shrunk it back to 22, that doesn't guarantee it release the memory. So that's the main thing with shrink to fit. That is dependent upon the particular implementation of the STL you're using. So stood vector on the stack. So everything we've been saying, stood vector allocates in the heap, right? And I have to say, this is a talk from the 2019 CppCon. For me, this was a deep talk. So one of the things, you know, what you don't always see is stood vector takes a type, right, as one of its default arguments. We tell it that it's an int, or we tell it what kind of structure we want. What you don't always see is that stood vector also takes an allocator. And so you can use custom allocators with stood vector. And this particular talk is interesting because they actually talk about using PMR allocators to be able to allocate your vector on the stack. And it will turn around and pull allocation from the heap if needed on a per call basis. So if you are interested in how to really get performance out of the allocator with the vector, that is one way to end up doing it, is check out this talk about using PMR. All right, iterators. Any of you love pointer arithmetic? Of course you do, Walter. So what is an iterator? I like to think of an iterator as basically a nicely wrapped up pointer that has guardrails. So in this case, I want to show the very first iterator that we have, you know, begin will get us an iterator or a pointer, that first element that we have there in the vector. And so as we see when this runs, COBegin gets assigned to it. That is a random access iterator in this case. I happen to know that because generally when it comes to stood vector, we have two types of classes of iterators that get used, random access and contiguous. Different container types have different types of iterators, and we'll look at that in a minute. As you can see, you can turn around and get the reference to the address or the reference to the item itself. So an iterator underneath, in this case, is a pointer, but it's not always a pointer in all cases. That's the thing, is it's an abstraction that is really based upon the type of iterator it is and the container kind of dictates the type of iterator that gets assigned to it. Again, vector, random access, contiguous a lot, but if you're actually using like a stood list, I want to say that's bidirectional because it's not a contiguous memory. It handles the iterators differently. So like I was saying, to me, this is what pointers are like. If you've never driven this highway in Colorado, it is an experience. Don't do it in the winter. No guardrails. I think it's like 70 miles. So an iterator, though a pointer can be thought of as an iterator, it allows us to iterate over elements in a block of memory. Iterators in the STL abstract away and, like I was saying, I feel give guardrails to a pointer. It allows us all the benefits of a pointer and helps prevent us from making mistakes. If you think of the for loop where I can count off the end, if I use an iterator by doing co.end, I'm not going to count off the end. I'm going to get an iterator that points to the end of the container. It's not going to be a problem. So it's a pointer in bubble wrap. So like I was saying, we do have different types of iterators. Forward iteration from begin to end. So here in the for loop, we start with COBegin and get that iterator. We make sure that we don't reach COEnd. I'm sure a lot of people are familiar, but if you're not, end points to the item beyond the last element. It's not the actual last element, but the item beyond it. But another thing that's kind of interesting is you do also have the rbegin and the rend iterators, which I honestly don't use that much. It's not too often that I've had to reverse a container, but they are available. And you also have the C versions of iterators, for the const versions, depending upon which ones you need. Either way, we end up getting our pointers, and we can then iterate through the particular data that we're working with there. So this is where I was joking that my favorite not iterator is a range-based for loop. So early on when I was learning the STL, this was one of my gotchas. I mistakenly thought that the range-based for loop was using an iterator. But as I noted on there, it's not. It's making a copy every time, right? And so there's some great times when I will use a range-based for loop because it's nice and it's easy. You pull the data out. But if you're actually trying to iterate through a structure and change the details inside that vector, you're going to want to actually use an iterator to do that, because the iterator actually points to the piece inside the vector, not taking a copy out just so that you can display it. They both produce the same result, but they do it in a different way. And the main thing, yes?
I was just going to say, you can have it be an auto reference, and then you can have access to the, like a non-const access.
That's true.
I personally like that better than the iterator.
So, performance or?
Yeah, performance, sure.
Oh, so do me a favor. Can you say that back on the microphone? Because you'll do a better job at.
Oh, I was just going to, you mentioned that you need to like modify the contents. You got to use an iterator. I said you can use a reference to, like I guess whatever the left side of that range-based for loop is, it can be a
you can make it into a non-const reference, and then you can end up changing it as well. Thank you very much. I like finding mistakes. I like learning things that I didn't know too. So I haven't done it that way that much, hence why I've learned. So thank you. All right, so I'm only putting this here. This is off CPP reference to show that there are, as I noted, there are different types and categories of iterators. The last two on the bottom are the ones that work with std vector. And honestly, I've seen people give talks about the different categories of iterators. I don't really develop libraries myself. I'm more of an application developer, so this isn't something that I get into that much. However, I do know, for example, that's where I was saying bidirectional iterator or forward iterator, they work for specific containers, and they're there for specific reasons. Random access iterator, because of the way that it accesses the memory, again, the iterator category, if you will, is more based upon the container and the features that you can end up using. For example, in a bidirectional iterator, you're not going to be able to get the random access, but that's also how a linked list is, right? You can't just turn around and pick to be in the spot in the middle of a linked list. You have to turn around and go forward or backwards to find the spot that you want. So that's our favorite, at least for me. We also have the legacy contiguous, but the random access is what std vectors relies on most. So the other thing that's interesting about iterators is invalidation, right? And so this has definitely caught me a few times. You have a vector of content that you're working with, you go through and you change one item, and suddenly all your iterators fall away and fail. And so here you can see we start off with a group of years. We take an iterator to CppCon years begin, which is of course going to point us at like 2020. I decide I want to put on, the future 2025. In the end, as soon as we do that pushback, our iterator becomes invalid. We changed the vector. That vector could have reallocated. If it reallocated, then the pointers all became invalid. So my easiest way of not getting into this kind of trouble is I just remember if I wrote to it, you need a new iterator. That's at least my way of thinking about it. And not sure about the side popping on and off. Apologies for that. So invalidating iterators is one of the big gotchas you want to watch. I won't necessarily cover it in this talk, but one of the things that we have in the standard algorithm is remove if. There used to be the erase idiom that we would use, where in order to erase an item out of the middle of a vector, you would first search for it, get an iterator to it, then erase that item. Of course, when you erase that item, you just invalidated all the iterators. And so that was the particular one that used to get me every now and then. I would be going through, a looping through something where I'm trying to delete out items, and as soon as you delete out one, you've basically invalidated every other iterator after that. And if you're in a big container of thousands of items, it's something that you have to consider and think about. So again, CPP reference. You'll notice for vector that this is a great table for all of them, but after insertions, iterators valid, yes or no. You can use this as a quick reference, but honestly, I still like my rule of, it's kind of like that if you broke it, you bought it. If I changed it, that's all there is to it. If I wrote to it, it needs a new iterator, or I need to get my iterator refreshed. So iterators, if you really want to learn to write them from scratch, Mike Shaw does a really great series on iterators. This is just one of the videos out of it. Like I showed at the beginning, it's not like we don't have a lot of YouTube content on vector and STL, but Mike does a great job with his videos, and there's the link for that one. All right, so algorithms. When I first started using vector, I wasn't using the algorithms as much. For me, it was storage. We would iterate through it. So I work for a company called EPX. We're a credit card processor. If you live inside the North America, continental US, there's a 60% chance that I've processed one of your cards when you swiped it at a gas station, a grocery store, etc. And so deal with thousands upon thousands of transactions a minute. Normally, we pull stuff out of a database. We kind of like to joke that it's like, when you're a back-end programmer, that's kind of like your life, right? You either get something from the internet, you change it and you shove it into a database, or you pull it out of a database, change it, and send it back out to the internet. It makes nice when you don't have customers complaining, but So anyways, with algorithms, the one part that I used to get stuck on when I would do them was this unary predicates. I'm not a terms person, but it's like, I need a function that just returns a yes or no. I know unary predicates sounds nicer, but unary predicates and iterators are used in pretty much all of the algorithm headers. And so we're going to do a quick little overview of some of that. And I'll see if I can't get us out of some of the toy examples after these first couple. So I'm going to do a couple of the predicates here because this was what kind of got me past. So when I first started learning to do standard algorithm, I was moving a program from, it was basically C++98 into C++11. Lambdas had just come out, and so the lambdas, I just wasn't grasping it yet. So I did a lot of functions. And so the first time I started to learn a predicate, I liked the idea of doing it as a function. So a predicate is, as noted, you're going to pass in a value, and it just returns a yes or no. And this is one of the things that we pass into a lot of the standard algorithms in order for it to make a decision as it iterates over whatever our container is. So in this case, if we take Colorado and all of the years, we can use the std find if algorithm. We pass in our two iterators, and you'll notice I use begin and end, and then I pass in the function is even. So every one of those years is going to be passed into is even, and as soon as it finds the one that is, we will get our output. And so as you see there, the first one is 2020, as we would expect. I definitely found it, again, for me, I start off writing, if I need a predicate, I'll put it as a function, and I'll start with it there. I do love lambdas, though. And so before I get to the lambdas, though, I want to point out that the thing with iterators, and part of the power of it, and this doesn't even get into ranges, which is a whole nother topic, which there's also lots of videos on. But if I turn around and take my initial iterator and add 2 to it, now you'll notice that I'm grabbing the next first even value, which is 2022. So part of the power of the algorithms is you give it your begin and end, you give it your predicate, and it's going to work within that range to get you what you need. Now, as I was saying, I started off by doing things as a function, and I left it up there in line 6 because originally the lambda syntax just didn't make sense to me. A lot of the benefit of the lambda syntax is that you don't have, it's right there. You can see when I'm calling find if, this is exactly what I'm trying to do. I'm trying to return whether or not something is even. I think it can be argued either way. in one hand, I actually like seeing the function that's saying is even, because to me that documents the code a little bit better. But I can also understand, depending on what you're doing in a function, putting the lambda just that way. And I do have code, in our own code base, we actually have named lambdas, if you will, or kind of more like a functor. And we've done that as well because it at least helps document a little bit better what your intents are. So as we've been preparing slides, because all speakers, we work on slides up until the last minute. On Discord, one of the speakers posted this at about 2 a.m. And that was his comment. He's like, at 2 a.m. when you're making slides like this, and he's like, I don't know if the slide will make the cut. So I said, thank you. I'll make sure it makes the cut in mine. All of the code I'm going to show next, I'm going to get out of the toy examples, and I tried doing something that actually looks a little bit more like credit card data that I use. All of it compiles, all of it built, all of it ran, and all of it will be checked in if you want to check it out. But I'm tweaking my slides to fit things in so that it looks nice. And so by all means, hit me up with questions. All right, so fun with algorithms. So like I said, I do credit cards. And so this is kind of a basic structure of a credit card, right? We have a type of card, Visa, MasterCard, or American Express, name, credit card number, CVV, expiration date, and the amount. And incidentally, yeah, in credit cards, we use longs. There's no floats. Everything is a long as it's passed as an integer. So, I got a simple print function there for output. So what do you do when you need test data? How many of you use OpenAI, ChatGPT, or any of them? Okay, so I thought this was pretty cool. I actually got on ChatGPT, gave it the JSON, and as you can see, the request that I said there, give me 2,000 elements. Sure enough, a minute later, I had a JSON file with 2,000 elements. Like, all right, that's not bad, except for I made a mistake. The amount there being 4593, it kept everything as a 4-digit randomized number. So then I had to go back and say, repeat the last request, but make my amounts bigger in a randomization. So sure enough, cut me back 10,000 of them. So then I asked for 100,000 of them. It took a little longer, but yes, I have a 100,000 structure file of credit card data with names and numbers and everything else. And so that's what we'll play with in this. And so I just got to say, I don't know how everyone else feels about ChatGPT and OpenAI. I don't use it inside my actual code. I'm not big on having it in we use VS Code at my daily work. And of course, working in credit cards, PCI compliance, no AI is looking at our code. That's just not happening. But I do love it for being able to go in and ask questions. I do think it's going to be interesting how things progress with AI. As you noticed, I packed, because I do some technical editing for them, I will say it's been interesting to see even the publication companies, how much they're actually taking their book libraries and feeding it into AI so that they can then turn around and have it be more of an oracle. So now instead, like I said, nobody reads the book front to back. You're literally just going to use their particular service to get access to their knowledge base that authors have written. All right, so we got a function here that's going to be called load card data. We'll pass it a file path. It's going to load it into JSON. If anybody use Enloman's library? All right. So I did a talk on it. It is not the fastest library, this we know, but it is one of the simplest and easy to use, which is why we end up using it. And when we started using it, it was a much more controllable single header file, which, if you're building software and you're ever worried something's going to fall away, you like having something your team can take over and manage. But I will say, yeah, Enloman, I do like the JSON editor. So we're going to load the JSON data. And so this is what our main looks like. So we're going to start with 10,000. We're going to load in 10,000 credit cards into a vector. And then you'll notice I got another vector there of just strings of Visa, MasterCard, and American Express. And so line 6, we're going to get a count to make sure the amount of items that load in, just so that we can see it. And then this isn't the algorithms header, this is numeric, but we're going to use std accumulate to actually accumulate the total amount per card type. And so when this ran, It took about 1.4 seconds. We had 10,000 items, as the original file was, and you can see the different totals for the values that it had there. I did not go through the 10,000 items and manually total it, so I'm going to just guess that it's right. We'll go with that. Either way, the more important part is, so this was 10,000 items in a vector. The next slide, I'm going to show you 100,000 items. For the last book, anyone want to take a guess at how much more time it took to do 100,000 items versus 10? Just give me a factor.
100.
1,000? You said 100?
Yeah, 100.
Okay. Anyone else? Similar time? Okay. It's not constant, so I'll give you, just as and it's not 100. 10? Do I have any others? For the, 2 times? Huh? So if I run this same algorithm with 100,000 items, how much more time do you think it's going to take? Right now, we have 10 times, 5 times, 2 times, 100 times. Okay, I was up all night doing slides. I'm not that great with my logs. One more? Okay. Did you have a suggestion? All right. So 2 times is closest. So 100,000 items, and we're at just about 2 times the amount. Almost always vector. I'm saying. Okay, so how does vector compare? So if you take std_list as a doubly linked list, you don't get random access. It's efficient for insertions and deletions. So that is the one thing that vector does not do. If you ever want to insert something into the front, you're just going to reallocate everything. It's just not that great at it. Inserting in the middle is also not that great. So vector is not, if you're pushing back on the ends, you're nice, fast, and efficient, but going to the front is not. However, std_list is higher memory overhead, and it's slower because it doesn't have the cache locality vector does, because vectors are contiguous. So you want to use std_list when you're doing frequent insertions and deletions at arbitrary positions. Personally, I start with a vector, because if I find something is slow, then I can easily change my container. It's not that hard. You're literally changing just std vector to std_list. Iterators and everything, you might have to adjust as you go, but I start with std vector. And with the deck, again, non-contiguous, but it does support random access memory. You can do fast insertion and removals on both ends, but it is far less cache efficient, and it uses a lot more memory. It's kind of a combination of a linked list with small blocks of contiguous memory. And that's how it keeps its support for random access, but it becomes less efficient. And so if you're going to do a lot of insertions and removals on the front and back, but you still want that somewhat random access, a deck is a good way to go. And I do know that, I'm talking about this from that kind of a performance characteristic. Obviously, there's the part where you're like, well, my particular algorithm, the way I'm doing something, I need to pop or I need to push, and that, of course, goes into account too. But, you can turn around, as we saw, I can get back on a vector. So if you're wondering which one to start at a vector and change it when you need to. So std_map, I was going to compare that one, and it's not scrolling. But I'll just tell you this. This one scrolled for almost as much time as the std vector did. So there's plenty of stuff on std_map, but std_map is an apple-oranges comparison because you're getting a key value with a hash map. Your lookups are incredible. There's lots of times I love using maps, but I haven't done a book yet where I'm doing the editing for maps, so we'll have to see. Okay, so why we almost always vector? So it's efficient, it's cache-friendly, fast access, it stores elements in contiguous memory, really great from a CPU and cache locality, amortized constant growth. It's just, though you do have your problem when it comes down to reallocations, you can still be smart and plan for those. Practicality, automatic memory management. I don't have to think about new and delete. If I'm doing it inside a function, it cleans itself up. If I need it to be accessed through, a larger part of my program, I'm putting it in a class or I'm putting it somewhere else that it can be reached. Random access. For the data structures and things I do, kind of like the short example I did with credit cards, in that case, I did a summarization of it, but there's lots of times where I actually, the first 6 digits of your credit card is called a BIN. And so that actually defines which bank your card is from. So there's actually times where I have to turn around and look inside of a vector and be like, I need every one of these particular bins. And the thing that's great with vector is it's easy enough to turn around and sort. I didn't show the algorithm for doing sort, but before I do that, the first thing I do is I do a sort on the whole vector, and then I can very quickly get to the spot that I need. And it gives me a bit more flexibility than a map in that case. And versatility. So I can't think of a place that doesn't have std vector anymore. After 32 years and everything that's gone into it, the dynamic sizing, flexible insertion, pushback, and place back, insert, which I use cautiously, it wins on versatility. So thank you. Almost always vector for the win. And I haven't done the push of the code that's right here, but I'll get it done by the end of the day. If you end up wanting to get access to any of the stuff, including the slides, you'll be able to find it there. Questions? Yes. And can you come to the mic?
So you mentioned that the square bracket access operator can introduce errors like in C, whereas at
you can catch, yeah.
Why can't we implement that? Like, why doesn't Vector implement error handling in the access operator?
Actually, I can't say that I know why. I don't have the reason why they didn't do it that way. I guess what I would say is that, on one hand, there's the argument that exceptions are expensive. Now, I will also say Khalil is giving a keynote this week about how exceptions are not expensive, whether that's from space or, CPU and everything else. I think part of it might just be historic. There's a lot of things in C++ where we keep it because we're still compiling stuff that's all the way back to C++ 98 and before. So that would be my best guess.
Thank you.
Yep. Anyone else?
So you mentioned sometimes we want to use std list rather than std vector, but I want to add one point that we still want to always use vector for deletion. If we do not really care about orders of elements in vector, which we mostly do not care, I think we can just swap the element we wanted to use with the back and then pop resize -1 of the.
You're absolutely right, and that's why I say almost always vector.
Yeah, so I mean, for that case, we still want to use a vector, which it echoes your point always, almost always.
Yeah, thank you. Is that it? Oh. Okay.
Mentioned that we can start at any point instead of at the beginning, so you
Yep.
+2. Okay. And then the for stop, the condition is the end of the iterator. So do you think if we put in an extra large number with the begin plus, will that lead to an undefined behavior because it'll start beyond the endpoint?
So yes, you absolutely could. So if I had this, and I know this isn't the slide you were talking about, but I think I can use it to reference. If we took this line 9 and had CO begin, and we actually did a +10 there, yeah, you would get an undefined behavior.
And is there a way to prevent that or catch that? Like I like the add. I think I'm gonna go back to my code and swap everything with my bracketing to add. But like, how do you present this?
No, I don't know a way that you would actually test that. And it's not, that was kind of a toy example. Like, there isn't that often that I would actually start with a CO begin and add 2 to get to a specific item. That example is more just to show the fact that it is an iterator, which is kind of like a wrapped up pointer. And so you can still do that pointer arithmetic-ish. But then that takes me back to the fact of anything I ever do with pointers, if I'm not careful, I end up taking off a limb. And so you can do that same thing. You could turn around and put CO begin plus 10 here and create undefined behavior.
Yeah, and you think that if it is a contiguous memory, then, and you know the direction you're, maybe the compiler could check for you, see like if your stop is beyond your start.
Yes, and it's interesting there because we have started learning that language nobody likes to talk about here called Rust. And watching the compiler and learning about the borrow checker and things like that, there are a lot of things that I can see. There's a lot of things that I've learned learning Rust that has improved my C++. But I think one of the benefits that we have with C++ is there are all these little, we'll say, sharper edges. But as we learn the sharper edges, then we get to make that choice. And and other things that I've seen, such as Patrice Roy does a great job talking memory management. And the way that we can tweak things to get that extra ounce of performance when you need it, there's a reason why so many things are still written in C++, and I think that's it.
Thank you.
All right. Thank you very much, everyone.